Technologies produces a video game engine that's quite popular, actually, especially in the mobile space. So these are just some games that you might have seen that are built using Unity, Pokemon Go, Hearthstone, Super Mario Run. Unity kind of exists a bit in the background, right? So their name isn't so much up front, but it's actually the case that a lot of games that people play are built. And about 10 months ago now, we started a machine learning team, and I joined when the team started. And kind of the thinking behind this team is this twofold idea, which is machine learning can be applied to games, and games can help feed back into machine learning and make machine learning algorithms better. And so with this kind of thinking in mind, we started to do some exploration around what machine learning and games might look like. And so the most immediate thing that came to a lot of our minds were things like this, where a lot of the work that's being done in the field of deep reinforcement learning. And so if you think about deep reinforcement learning and you think about games, at least what has been in the news a whole lot this past year is the AlphaGo algorithm. This is it, playing against Lee Sedol, the world champion, who had defeated. And then on the left, it's just an image of Atari. And so a lot of the deep reinforcement learning work that kind of kicked off people's interest in it was around being able to play Atari games. So we wanted people to be able to do this using the Unity engine as well. And this is where the idea for what we call the Machine Learning Agents Toolkit came from, which this toolkit is essentially a way for people to take a Unity project, a game maybe that they're working on, or something else, a simulation, and turn it into a training environment, a test bed, a playground for doing machine learning research. And now I just want to kind of start off with one of the first demos we did. What I first did kind of when I joined Unity was put this together as an example of the fact that it was possible to do this kind of work within the Unity engine. So I built this really simple game. It's kind of like Frogger clone for those who played Frogger, or Crossy Road clone for those of this decade. So basically, you control this little character in the middle, or the agent, the algorithm controls the character. You have 4 possible moves: up, down, left, right. Getting the agent reaching the present gets +1 reward. The agent hitting a truck gets -1 reward. And then we use the DQN algorithm to try training this. So we do it from pixels. So you take the screen input, and then from that you produce 1 of 4 actions: up, down, left, or right. And so the way these algorithms work is you initialize the neural network to a random policy at the beginning. So what you start out with is essentially purposeless action, right? Just running around in circles. This is what it looks like. And then eventually the agent starts to hit things, get positive or negative rewards, and this serves as a reinforcement signal, which pushes its actions towards the goal, towards positive reward. In this case, that means pushing it towards getting more and more presents. And so this is after an hour of training. It's already gotten a little bit better. It's pretty good at getting the presents, but it still kind of hits the trucks. Now after 6 hours of training, this is fine. It's really, really good. It goes very fast. It hit the truck there, but it's not going to hit the truck again. And so essentially we have this relatively simple game, but already with only 6 hours and without hand coding any sort of AI behavior, we have something that's essentially superhuman. That bit at the end, that's the best part. And so we were kind of very encouraged by this, to see that these simple games with reinforcement learning and not so much hyperparameter tuning, not so much thinking about it, could actually get interesting behavior out. Now, if you're someone who's a little bit familiar with this field, you might say there are actually a lot of reinforcement learning training environments, scenarios. What is Unity necessarily bringing to this? What is our thinking around this? if you survey the landscape as it currently exists, there are a lot of really great solutions from different groups, and I think that they all kind of tackle different kinds of problems. So this is just a survey of some of the most recent ones in the past 5 or so years. We have the Minecraft environment that lets you do ML research in Minecraft. There's PyBullet, which is really great for doing robotics work. Then recently DeepMind, for example, released the StarCraft 2 learning environment, which let you plug in agents and try to beat StarCraft 2 games. So there's kind of all of these around. And I tend to break them down into 3 groups, which kind of correspond to maybe like psychological categories or something like this. So that would be visual complexity, physical complexity, and cognitive complexity. So what I kind of mean by each of these is visual complexity fits into more the traditional domain of computer vision. So what is the fidelity of this environment? How realistic is it? People doing things like self-driving cars are very interested in this, right? So you want to be able to, if you're training in a simulator, you want the simulator to look a lot like the real world. Then there's physical complexity, which people in robotics care a lot about. So the 2 environments I have here are the PyBullet and the Mojoko simulator. These are used a lot for robotics research. And they're extremely high fidelity in that you can simulate a robot walking in the simulator, put the same model into the real world, and as long as you're properly simulating that robot, it'll now be able to walk around in the real world or do whatever it's supposed to do. The issue here is that, as you might see, they're relatively simple-looking environments. The focus of these is physics quality, but not on visuals. And then this 3rd group I think of as cognitive complexity, which is, it doesn't even matter how it looks. It doesn't even matter if it has real physics or something like this. But what matters is how much strategy is maybe involved, or how much you really have to think about the task. So obviously the game of Go falls into this. Go is a black and white board. It doesn't matter that the stones bounce or anything like that. What matters is being able to think 50 moves ahead, right, and be able to come up with the right decision. It's kind of similar also for Atari. So I have here one of the Atari games that's still unsolved, Montezuma's Revenge. If you look at it, it doesn't look very difficult. It's a simple black and white, well, not quite black and white, maybe like 8-bit color game that still hasn't been solved by even kind of the most state-of-the-art algorithms. So all of these are great, but if we think about what Unity has to offer, the kind of games that have been released, say, in the past year on Unity, the Unity platform, what we find is that we are very excited to think about the fact that they kind of hit all 3 of these checkboxes. So they're visually very realistic, very complex. You have complex physical interactions, characters that are animated in very realistic ways. And then lastly, of course, because they're games, they are all designed to provide interesting cognitive challenges to the people who play them. So with this in mind and kind of that original proof of concept experiment working, we went to work on what we just released about a month ago, which is this beta version of an open source toolkit for doing this kind of research within Unity projects. And it's available up on GitHub. And this right here is just a very basic diagram of the way we were thinking about it originally. So if you've worked with something like OpenAI Gym, it's going to be very familiar to you, where you basically build up this Unity project. And then from Python, you'll be able to launch it and interact using all your favorite machine learning algorithms like TensorFlow, PyTorch, Caffe2, or whatever else you want to do. Now, this is just a diagram of, within the Unity side, how we're thinking about things. So if you have used something like OpenAI Gym, what you find is that there's thinking where there's the agent and there's the environment, and the 2 are very tightly coupled, and you don't really get beyond that. And when thinking about what people really want, especially interesting multi-agent scenarios, we realized that we should probably design something with a little bit more complexity. So what we have here is this system where you have agents, which are the things in your environment that perceive the world and take actions. You can have a whole bunch of them in a scene. And then you have brains, which is actually what does the deciding. So these brains correspond to parameterized models, often neural networks, in our cases at least. And you can have, for example, a single brain picking the actions of 10 different agents. This might make sense in any sort of game where maybe you have you're fighting enemies, you're fighting wizards, and you're fighting goblins, right? And all the goblins have the same brain, and all the wizards have the same brain, which really just means that they decide in a similar way. And lastly, we have this idea of the academy, which kind of ties everything together. So diving down into these brains in particular, we designed the brain architecture to be kind of like modular and extensible. So we are shipping initially with these 4 kinds of brains, which allow people to kind of swap out the way that these decisions are made. So we have the traditional way of picking decisions, which is just the player puts in input, presses the keys, very normal. Then we have what we call the heuristic brain, which is the traditional way of doing game AI, which is someone sits down and hand codes some behavior. Then we have the external brain. And so any brains in a scene that are set to external are now going to have their states sent out to Python when you launch it from Python. And they're going to have their actions decided by that Python side. So this is where the training happens with external brains. And then lastly, we're interested not only in this being kind of a research test bed, but also eventually in providing this as the kind of thing that game developers can use themselves once you have these parameterized models to put them back into the games. So we have this thing called the internal brain, where right now we're only supporting TensorFlow, but we're really interested in figuring out the best ways to expand beyond that, where once you've built the model, you can take that model, freeze it, and embed it back into the game itself, and then run it on things like phones. So here are just some things that are kind of made possible by thinking outside of the one agent, one environment situation. You can, for example, train multiple agents at once. And what this gets you is essentially more data than you would otherwise. So here, this is a simple task where the goal is to try to balance the ball on the paddle. And before training, of course, a random policy just knocks it over. Training with 12 agents at once, we can very quickly get to a policy where the agents are able to all keep the ball balanced on the platform. Then we can also start to do kind of fun stuff like have adversarial scenarios. So, AlphaGo was in the news for learning how to play against itself without any human demonstrations. Here we're doing something kind of similar on a much simpler scale, where we have these 2 tennis-playing agents that learn just by playing against themselves how to hit the ball back and forward. And kind of the cool part about this is that you have these 2 agents. They start out with the same random policy. They play against each other for a few hours. They get good with playing against each other. And then because of our flexible brain system, you can swap the brain of, say, the agent on the left out for a human brain. And now you've got a video game that you can actually play, where the opponent is controlled by a neural net. And kind of taking this a little further, while we haven't put together environments yet that do this kind of thing, the system is fully designed so that you could have competitive, cooperative, multi-agent systems, or even what we think of as ecosystems, where you have a whole bunch of different kinds of agents, each controlled by differently parameterized neural nets within a single scene, all interacting with each other. Okay, I'm going to talk a little bit more about some of the features we built in and just kind of some of the ideas around what we think of as being useful for doing this kind of research in the future. So like curriculum learning, for example. This is essentially the idea that if you, especially with reinforcement learning, you start out with a random policy, and a lot of the time, a random policy is never going to get you anywhere, no matter how hard you try. So for example, in this task where the goal is to jump over the wall and get to the goal on the other side, and the agent is the little blue cube there. If you had a completely random policy, the correct solution is to hop onto the this little platform, and sometimes the platform is over here, so the correct solution is to push the platform over, jump on it, and hop over. If you think about completely random series of actions, the likelihood of that random series of actions ever leading to you doing that is extremely low. But if you start with something easy, like say there's no wall at all you have to do is randomly happen to walk up to the little green square, then an agent can learn that really easily. And now if you have a parameterized model that knows that running up is good, hitting the square is good, you can start to build a little bit higher wall. Now all it has to do is jump over a little tiny mound in the ground. Then you can progressively make it more and more difficult. Same thing on the right side, it's this little pushing task. And so this is just the agents, the fully trained curriculum learning trained agents doing each of these tasks. And the point of this video is just that they can do them. But if you were to try training these final versions of the task from scratch, either they wouldn't be able to do it or it would take kind of 10 times longer. Another thing we're really interested in, because of the fact that this is a game engine and we can control everything in the game engine, there's the notion of cameras. So you can basically put cameras in a scene and those cameras get rendered. So in the case of a multiplayer game, you can get the view from multiple players. But also in the case of something like a self-driving car, you might be very interested in getting both a front-facing view and a rear-facing view out of your simulator. And so just as a very simple experiment for this, we set up this map reading scenario. So I'm going to do my best to quickly explain this. It's best to think about this observation. So basically we have these two cameras. We feed them both into the same neural net. One is a first-person view, kind of very typical. This other one is this abstracted map view of the goal and the landmarks. So it's best to think about this as like a paper map that isn't specific to you at all. So you drop an agent in a scene, you give it this paper map. The goal is to basically learn to integrate both views. So in the same way that if you're a self-driving car, you want to integrate what's in front of you, what's behind you. In this case, we want to integrate what you actually see and where the goal is marked on the map.
The map is rotated.
So the map is fixed.
Relative to the observation.
No, that's why so it's a complete paper map. So imagine the map is not at all tailored to your own personal point of view, right? So in the case of the agent, you have to learn to mentally rotate the map, mentally place yourself on it, and then use that, yeah. So the reason that this would be, so here's a little video of it playing. This right here is for visualization purposes, that shows you where the agent is and where it's looking, but the agent itself doesn't get to see this. It's just so that all of you can see it. Let's see. And this video is just to show that it learns to complete the task. But what's interesting is that, for example, right here, the agent doesn't get to see the present in its own first-person view, yet it knows exactly where it needs to go next to get to the target. And like this, yeah. So we think this is kind of just a cool example of the fact that we can use multiple cameras in interesting ways that a lot of researchers maybe aren't doing right now because of the limitations in their own platforms. There's not so much time left, but we have these monitoring features built in which allow people to visualize outputs from the network. So here is that tennis game again, and what's above their little heads is the value estimates for each of the agents. And so the value estimate corresponds to how much reward the agent expects to get in the future. And you can see that while both agents are doing well, they're both hitting it back and forth, they have positive value estimates, which means that they both think they're going to keep getting a reward. But you're going to see, and you already saw it once, but this agent, when it makes the wrong move, when it hits it in such a way that it's not going to be able to hit it back again, its value estimate immediately goes to 0. So we think this is an interesting way to be able to debug these algorithms where you can kind of visualize what they're thinking about in real time. The Unity engine as a platform is also very extensible. So we have the asset store, which is filled with all sorts of assets which people build and sell, like cars, any sort of 3D model, environments, towns, cities, all simulated. And image on the bottom is just showing the fact that people also even make entirely different physics engines and offer them as plugins to Unity. So in the bottom, that's the bullet engine. So if you said, oh, I don't like Unity physics, well, that's okay, because you can just plug in another physics engine and use that one. Now, the training workflow is essentially Unity to Python to Unity. So I kind of mentioned briefly this idea of putting together your scene. So this is that balance ball scene I had before. You essentially would, from within the editor, download the plugin, drop the plugin into your project. Then you can add these scripts to your scene, which turn your scene into one of these training environments. As far as kind of filling out what is special about your own environment, there's this agent template, which you basically fill out what the agent's states are, what the agent's actions do, what the reward function is in that environment. Once you do all that, you build up the project, and you're ready to launch it from Python. So we have a nice little Python API, which is very similar to the OpenAI Gym, if anyone's used that. And you can essentially just launch it, call the executable file that you built, it's the Unity project, and then it gives you all the specifics about that scene. And you can do things like reset the scene, step the scene, similar things to OpenAI Gym. Yeah. Now we ship with a reinforcement learning algorithm that I quite like. It's called proximal policy optimization. I would say that in the past few years, one of the big problems for making deep reinforcement learning mainstream is that all of the algorithms only worked if you were at the scale of Google, and you could do hyperparameter testing for a month. It's finally the case now, I would say, within the past few months, that there's algorithms like PPO that anyone can kind of pick up, and without too much hyperparameter tuning, they'll actually work on a variety of problems. So we're kind of excited about that. We have a version that I had implemented that you can just use. So you use that to train your model or whatever else you want to do. Then once you've got the fully trained model, you can freeze it and drop it back into your Unity project. So what I'm showing right here is this is the inspector window for a brain. And it's pretty hard to tell. Maybe it's easier there. But you can set the type of brain to internal. And then you can drop in that frozen model. And you can use that to now control that agent on Mac, Windows, Linux, iOS, and Android, which are the 5 platforms that TensorFlow currently kind of by default builds for. Now, where do we see this being useful? I'd kind of already mentioned the research case, but in addition to this, we think that robotics and autonomous vehicles can use this as a simulation environment. And of course, lastly, being a company that's very much rooted in gaming, we hope that people within the gaming industry can find it useful as well. So as far as the research case, a lot of work around deep reinforcement learning. People are very much interested in solving AI, whatever this means. But basically, there are a whole bunch of unexplored problems, a lot of them, I think, around multi-agent interaction and communication that people are only really beginning to start to do any work on. And I hope to see some of that work in Unity, or just more of it in general. There's also then the industrial use cases. There are a number of automakers, for example, who are interested in or starting to use Unity as a platform for simulating self-driving cars. We think that this can be useful also for things like robotics. So this is just a really quick 2 images of taken from a study done earlier this year where people used Unity to train a robot, kind of Roomba-like robot, to navigate around a simulated apartment. They then took that model, fine-tuned it a little bit, and it was able to navigate around within a real environment in a real robot. So this kind of sim-to-real stuff, while it's still somewhat early on, is at least there are kind of proof of concepts out with it, and proof of concepts involving Unity too, which is cool. Lastly, as I mentioned, we're still very much a game company, so we think this can be useful for games as well. So there's the obvious case of, oh, you can use this to control your game AI, which we think is kind of cool. But there's also a lot of work being done in VR and AR, where computer vision models are very important, and having computer vision models that can deeply integrate within a game engine can be very useful for things like object detection, image segmentation in real time. Lastly, I think one of the more applicable places, but maybe things people don't think so much about, is around QA testing in games. So right now, if you build a game, if it's a really big game from a AAA studio, you're probably going to have dozens to hundreds of QA testers playing your game nonstop, which is kind of a lot of time and effort. And we think that by using things like reinforcement learning algorithms, you can have agents which essentially play your game and find the bugs for you by trying to optimize for whatever they're supposed to optimize. So a quick example of that is going back to the wall jump. When I was building the collision detection for the wall jumping game, I had thought that I had gotten it right. And then I set the RL algorithm on it. And what it realized is no matter how tall the wall was, if it hit the wall just perfectly and made a jump, it could fly into the sky and go all the way over the wall without having to use the block or anything. And so obviously that was a bug in my game, and I didn't have to find it. I didn't have to have any human find it. Just by having the agent try to beat the game, it found it for me. I was able to fix it and then kind of move on. So I think this cycle can be useful for game developers as they're kind of building and prototyping games. So lastly, this is just a few of the things that people have built that I've happened to find on Twitter in the past month since we released the toolkit. They're just a bunch of kind of relatively simple games, but it's cool to see a bit of diversity in terms of people making robotics things, infinite runners, breakout kind of games, racing games. I'm excited to kind of see where people go from there. Yep, so that's it. I would encourage anyone who's maybe interested to try it out. It's on GitHub. We're very much interested in getting feedback from people who actually think that this might be relevant for one of their use cases, but maybe say, oh, this is terrible, it needs to be different. We're definitely interested in hearing that too. Great, thank you.